Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to analyze a simple DC circuit here that has only a single voltage source and a pair of capacitors in series. So what we have here, I've got this picture where I've got this 12-volt battery switch in the circuit hooked in series to a pair of capacitors here, a 2 microfarad capacitor that I've called C1 and a 8 microfarad capacitor that I called C2. What we're going to do here is imagine that the switch is closed, and we're going to try to calculate the charge and voltage on each capacitor. So first, let's, in our picture here, close the switch. Right, now that the switch is closed, let's think about what's going to happen. Remember, this terminal right here is positively charged. So what it's going to do is it's going to pull electrons. And electrons in this region are going to want to basically move over to this plate. And that means that electrons move everywhere throughout this entire circuit, all the way to this point. So we're going to have electrons leaving this plate, electrons coming onto this plate. So when we have this transfer of electrons, that's going to give us charge configurations now on these capacitors that are going to look like this, plus, minus, plus, minus. Because again, electrons essentially have moved clockwise through this system. Now again, when you're talking about circuits, you usually talk about positive charge transfer. It doesn't really matter if you think about the electrons moving or you imagine positive charge moving. So when you write equations though, you assume positive, when you assume currents, you assume positive charge carriers for the current, because the positive current direction is defined around positive charge carriers. All right, so now we've got charges on, we got a charge on this capacitor, which I'm going to call Q1, and we have a charge on this capacitor that I'm going to call Q2. Now, I'll talk about how they're related here in a minute. Another important thing with these problems is potential differences. And if you've seen my videos, you know I love color coding potentials here. So this is the highest potential in the problem. I'm going to color code this red, and this red is going to be good all the way to this point because this is all conducting material up to that point. Now, the capacitor itself, we're going to have a voltage drop across it, right? So this color now is going to be at a lower potential than red. I'm going to go ahead and make that orange. That's going to be good up to this point. Then we're going to have a voltage drop across this capacitor as well. And then this is all going to be one potential, so I'll just leave that black. So you'll notice we have three different potential differences in this problem: red to black, red to orange, orange to black. Now, first what I'm going to do is I'm going to simplify the circuit down using the idea of equivalent capacitance. So this pair of capacitors is in series. We can find the equivalent capacitance by taking, oops, do this in black. 1 over C equivalent is equal to 1 over C1, which is 2 microfarads, plus 1 over C2, which is 8 microfarads. So when we solve this for C equivalent, I get 1.6 microfarads out of that. Now, a little reminder about a farad. Right? Capacitance is defined as charge per unit voltage. So a farad is a coulomb per volt. All right, so this pair of capacitors in series is equivalent to a 1.6 microfarad capacitor. So what I'm going to do now is redraw the picture. Start with my battery. Here's my switch, but it's closed. And I'm just going to put a single capacitor now, where that capacitance is 1.6 microcoulombs. Now we have a certain charge on this capacitor, and again, when a capacitor is charged, what we mean by that is we've got a plus Q on the right, a minus Q on the left, so it's really a difference in charge between these plates. All right, and we can now calculate this, and the reason we can calculate this is because the red potential is good to this point. So you'll notice that red to black is 12 volts in my problem, and I have red to black here. So the potential difference across my equivalent capacitor is 12 volts. So capacitance is equal to charge over voltage. So the charge on that capacitor is going to equal the capacitance, 1.6 microfarads, times the potential difference across it, 12 volts in this example. and I get 19.2 microcoulombs. And remember that a farad is a coulomb per volt. All right, so we got this charge now, 19.2 microcoulombs. Now that's the charge on my fictitious capacitor here, the equivalent capacitance I put in. And let's talk about how that relates over to here now. Now remember that electrical current flow is a lot like water through a garden hose. Basically, if 10 electrons moved off of here, 10 moved off of here, 10 jumped onto here, 10 left here, 10 jumped onto here, and so forth. The same amount of charge, if I go through this circuit and I look at some cross sections here, 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 the same amount of charge has to go through each cross section. So what that tells me in this problem is the charges Q1 and Q2 must be equal, because although I didn't state it, I had intended on this to be both of these starting with zero charge. So Q1 is equal to Q2 is equal to 19.2 microcoulombs. Remember that when you're dealing with capacitors that are in series, the charge is the same on them, if they all started with the same charge, by the way. And I'll look at an example here where they start with different charges next. All right, now what's not the same is the voltage. You'll notice that the voltage across here is red to orange. The voltage across here is orange to black. We can calculate voltages here and here right from the definition of capacitance. Capacitance is charge over voltage, so it's pretty easy rearrangement of this equation to say that voltage is equal to charge over capacitance. So the voltage across here is going to equal the charge on that capacitor, 19.2 microcoulombs, over the capacitance of 2 microfarads, and I get 9.6 volts out of that. I'll call that V1 for the voltage across capacitor 1. Now, at this point, there's two different ways to get the voltage across here. Method number one, we could just reapply this equation, which is what I'm going to do. Method number two is we could use the fact that black to orange potential plus orange to black has to equal black to red, which is 12 volts. But what I'm going to do is I'm going to save that for a check with my work. I'm going to go ahead and calculate the voltage across here, call that voltage 2, by taking the charge on that capacitor, 19.2 microcoulombs, dividing by its capacitance, 8 microfarads, and I get, what do we get out of that? 2.4 volts. Now, you'll notice that voltage 1 plus voltage 2, that's adding this and this, these add to 9, 10, 11, 12 volts. And there's my check here that I think I'm in pretty good shape for this problem. So, again, the intention of this problem was just how to work a very simple series circuit with capacitors. Hopefully this has demonstrated that reasonably well. Have a great day.